Morning, everybody. Welcome to the High Energy Density Science Center Seminar Series. I'm pleased to have with us today Dr. Debbie Callahan of Lawrence Livermore National Laboratory. Debbie came to the lab as a graduate student at UC Davis in the Department of Applied Science, sometimes known as Tiller Tech. Her thesis and postdoc work were modeling ion beam dynamics in an accelerator for inertial fusion energy using a heavy ion beam driver. In 2003, she moved from IFE to work on NIF target design. Her expertise is in Hohlraum physics and design, and she has participated in NIF experiments since they started in 2009. She is a fellow of the American Physical Society and a co-recipient of the John Dawson Award for Excellence in Plasma Physics for work done on NIF. She was responsible for the Hohlraum portion of the hybrid strategy that led to the recent high-yield experiments on NIF. And she's currently the Associate Division Leader for HED ICF Design in Design Physics Division and leads the Designer Training Program. So today's talk is being recorded. So if you're not comfortable with that, please log off. Also, it is an unclassified meeting and open to external participants. So please be aware of also have any export control issues. If you have any questions, you can enter them in the chat field, and I will read them at the end. Or if you prefer to ask your question verbally, just make a little note there, type the letter Q or something, and I will call on you. Otherwise, I hope you enjoy, and please take it away.
Okay, thank you, Paul. I assume you can hear me.
Yes.
So it's my great pleasure today to share with you some of the results, recent results on the National Ignition Facility laser, where we've achieved a burning plasma, which is also igniting by most definitions, and I'll explain that later in the talk. And this is a reprise of a talk I gave about a month ago at the APS Division of Plasma Physics meeting. So the work that we're going to describe here builds on decades of research by an incredible team from across the lab and our wider community. You can see some of the logos of the different organizations that participated in getting us to this point. It's definitely a team effort. It takes a village to get ignition. So the August 8th NIF shot, which we call N210808, yielded more than 1.3 megajoules and marks a significant advance in ICF research. On the left, I'm showing a plot of the fusion yield as a function of calendar year since we started doing layered implosions on the NIF back in 2011. And so you can see the progress that we've made over time, and you can also see that something pretty special happened on 210808 with the 1.35 megajoules. So this shot has a capsule gain, that is a fusion yield divided by the capsule absorbed energy of greater than 5. It's actually close to 6. It has a laser gain, that is the yield divided by the laser energy that we put into the target of 0.7. We had burn propagation with about 2% of the fuel burned up. And it represents a 13 times increase in fusion yield since the APS conference in 2020, which I've marked here on the plot. So this is really exciting. Our field is in a place that we've never been in before. So to remind you, inertial confinement fusion can be achieved by using high power lasers to drive a spherical implosion. So the lasers produce X-rays, which rapidly heat the surface of a capsule that contains the deuterium and tritium fuel, which we sometimes call DT. The blow-off plasma accelerates the DT fuel inward with a rocket-like reaction. So basically, we're making a spherical rocket. And that rocket converges on itself and the fuel stagnates, creating a hot central core surrounded by a dense confining shell of DT fuel. And if we do everything right, the core ignites and the fusion burn propagates into the dense shell and yields many times the input energy. So the US is pursuing several complementary approaches to ignition and ICF research. We look at laser indirect drive, laser direct drive, magnetic drive, and double shells. So this talk is going to focus on laser indirect drive. And achieving ignition is a scientific grand challenge that's nearly 60 years in the making. Okay, to do this, we use NIF, which is the world's most energetic laser, which enables the studies of extreme conditions for stockpile stewardship. NIF is an amazing facility, 192 laser beams, 1.9 megajoules of laser energy, and 500 terawatts of power. So using that laser, we're able to heat and compress matter to extremely high temperatures, densities, and pressures. And very importantly, we have a large number of diagnostics, more than 120 diagnostics, so that we're able to study that plasma that we've created in these extreme conditions. So the 192 laser beams of NIF are concentrated into a cubic millimeter scale target. So in the background, you see an engineering drawing of the NIF with the roof taken off, and you can see the two laser bays, each with 96 beams. And the size of the laser is about the size of 3 football fields. You can see some little cars here for scale. We take all of that laser energy and we concentrate it into a Hohlraum. Up on the upper right, I show a picture of a Hohlraum. It's about 1 centimeter long. We'll talk a little bit more about that next. And then inside of the Hohlraum, there's a capsule, which is shown on the lower right. The capsule is about 1 millimeter in radius, and that's what contains the deuterium tritium fuel. So indirect drive uses a laser-driven Hohlraum to compress the fuel pellet to the conditions needed for ignition. So we take those 192 laser beams from NIF and we focus them on the inside wall of a Hohlraum. So the Hohlraum is a small cylinder with holes at the top and the bottom where the lasers enter. We call those the laser entrance holes. And the Hohlraum is made up of a high Z material like gold or depleted uranium. So we put 96 beams in the top and 96 beams in the bottom, and those lasers heat that inside of the Hohlraum and create X-rays. And the X-rays flood the Hohlraum cavity, so we basically have like a little X-ray oven. And those X-rays then ablate the outside of the capsule, and that accelerates the fuel inward at speeds up to around 400 kilometers per second. The fuel core then compresses on itself and it reaches densities of 500 to 1,000 grams per cc, and it ignites at temperatures greater than 5 kilovolts. And if we do everything right, that fusion burn spreads through the compressed fuel and yields many times the input energy. So that's what we're trying to do. Okay, so what is ignition? In order to get ignition, which is a thermal instability, the plasma needs to have alpha heating greater than all the energy losses for a duration of time. So on the left, I show a cartoon of the imploded core. So in the center, there's a low density hot spot, and then it's surrounded by a dense shell of fuel, which is shown in blue. And the fusion reactions in the hot spot generate alpha particles, which stop inside the hot spot and further heat the plasma. So if you look up at the upper right at the time-dependent heat balance in the hot spot, you see the time rate of change of the temperature depends on that alpha heating that we just talked about, the alpha particles stopping and adding energy to the system. And then there are some losses. There's an X-ray loss and there's also a conduction loss, and those cool the hot spot. The last term is PDV work, and on implosion, PDV work heats the hot spot, but on explosion, it actually cools the hot spot. So we get ignition when the alpha heating term is dominant. And in that case, then you get a thermonuclear instability where the temperature rises very rapidly over a very short time. So what we're trying to do is engineer a situation where that heating dominates over the losses. So the targets that we use are engineering marvels. On the upper left, I show a photograph of a target. You can see this is the Hohlraum. It's about 1 centimeter long. You can see the laser entrance hole at the top. There's one at the bottom as well. And these black structures are the cooling arms that are used to cool the target to cryogenic temperatures in order to freeze that deuterium tritium in the capsule. Below that are just some fun pictures of the target before and after. So on the before picture, the business end is down here. I think you can probably see my cursor. And then you have the cooling arms that cool the target and attach it to the cryogenic positioner. And so before the shot, we've got the target here. After the target is gone, you can see we've bent up this metal. There's like some loose wires hanging around afterwards. And then on the right, I'm showing a view of the capsule through the laser entrance hole on the cryogenic target positioner. And this is where we form that DT ice layer. And so you can see in this image, which actually is from the 210808 shot, there's a ablator shell, which is the outside shell. In this case, it's a high density carbon or diamond shell. And then inside it, you can see the DT ice layer, which has been formed inside. The capsule is just over 1 millimeter in radius, and if you have very good eyes, you might be able to see the fill tube at the bottom. That's the tube that we use to put the DT inside the capsule. For this shot, that fill tube was 2 microns in size, and if you're not used to thinking in terms of microns, a human hair is about 100 microns. So this is an extremely small fill tube. So we've made progress towards ignition in steps, learning what limits the implosion and then redesigning based on that learning. So again, I'm showing that fusion yield versus calendar year plot, and now we're not showing the most recent shot so that you can see this a little bit better. But what has tended to happen is when we start a new design, we make rapid progress in performance, and then we hit a limiter. And so you can see that actually quite clearly in the high foot, which is the green bars. You can see that we quite rapidly, the yield started to increase, and then we hit a limiter. And then we need to do some work studying what's limiting and develop a hypothesis for what limits the design. And then we develop a new design that addresses that hypothesis, using data, simulations, and theory. And then we start a new design, and we go around this loop. So the NIF diagnostics have provided key insights into our experiments and helped us build understanding. Here are a few examples. The ones that we're showing here are mainly focused on the capsule. There are also diagnostics that look at the Hohlraum and the laser. But we have multiple diagnostics that measure that DT neutron yield. We have measurements of the ion temperature, the hotspot velocity, the density, the burn width, how long that burn duration is, the bang time. And then we have a bunch of imaging diagnostics that help us understand what that imploded core looks like. We have X-ray imaging from 3 lines of sight that tells us what that shape of that hot emitting region looks like. We also have spectroscopy to look at whether there's any high Z material mixed into the hot spot. Then we have neutron imagers that allow us to look at where the neutrons are being produced, and we have downscattered images that let us look at what the shape of the fuel is around the hot spot. We have a DT fuel map, which is basically an array of nuclear activation diagnostics that are right around the chamber where we can measure the yield, and that tells us something about the fuel uniformity. And a relatively new one is we've got Compton radiography, which uses high energy X-rays that are produced by the arc laser to make a radiograph of the DT fuel close to stagnation. So this is really the best diagnosed HED plasma on the planet. And this has been developed by over decades by the whole HED community. So our ability to diagnose the 3D aspects of this implosion has significantly increased from 2016 until today. So back in 2016, we had multiple lines of sight for X-ray imaging of the hotspot. but we only had one line of sight for neutron imaging, and we only had 17 of these yield uniformity detectors arrayed around the chamber, and we also had some limited spectroscopy. When you fast forward to today, now we have 3 lines of sight for the nuclear neutron imager. We've got Compton radiography, as we mentioned before. Of course, we still have the X-ray imaging. We have better spectroscopy. We have 5 Cherenkov and Entov lines of sight, which tell us about the temperature and the hotspot velocity. And we have 48 of these yield uniformity detectors arrayed around the chamber. And so with that, we can actually make 3D reconstructions of what the compressed core looks like from data. That's really exciting. So these improved diagnostics theory and simulations are all really key to developing our understanding. So neutron yield is a function of 6 parameters that we need to control to get ignition. And so we use scaling laws that come from theory, and in particular, this scaling law is for yield amplification of about 2, which is where we were until recently. And we use that to guide our design choices, although we need to test it experimentally because it doesn't always work out exactly the way the theory says. So let's walk through those six parameters that we need to look at. So the first one we're going to talk about is velocity, the implosion velocity, and you can see that the yield is a quite sensitive function of implosion velocity to the 4.5 power. So we need high velocity of the shell to produce that PdV work that heats the hot spot. The next one is scale or size, and it's also a strong function of the scale, and a bigger hot spot has more energy, so that's good. But we need to compress this shell very symmetrically. And so we need good symmetry to efficiently couple that shell kinetic energy into PdV work to heat the hot spot. If we're not symmetric, then that's a degradation that takes away from getting us to ignition. We also need ablation pressure in flight, and we do that by controlling what we call the coast time. We'll talk about that quite a bit actually in this talk, but basically what that means is that we need to keep pushing on the shell until very late in the implosion trajectory, very close to the time of peak compression. So lower adiabat or entropy is more compressible, and that actually reduces the energy we need for ignition, but it also makes the implosion more sensitive. And so far in our experiments, when we've tried to go to lower adiabat, that has not been as successful as a scaling like this would say. And so that's an area for active research right now, is understanding why that is. And we also need good stability because mix from hydrodynamic instabilities brings higher Z material into the hot spot, and that increases that radiative loss term that we don't want. So we've steadily advanced our physics understanding and the technology over the last decade to improve performance. So we're going to walk through the different designs, and we're going to look at them in this space, which is hotspot pressure versus hotspot energy. And hotspot energy times pressure squared is a ignition figure of merit, and it's related to the ITFX and the generalized Lawson criteria, which are other ignition figures of merit. So this metric uses no burn quantities. Basically, we're turning off the effect of alpha heating on the implosion. But of course, the real world burn is on, and so we use a model to convert the data from burn on to burn off. We also do dudded fuel implosions, which don't have a lot of alpha heating, to check that model. And we've done a couple of those, I think most recently sort of in 2019, I believe. And there's more experiments coming to do that again. And our simulations indicate that ignition corresponds to yield amplification of about 15 to 30. And so that boundary, of course, is uncertain because it's based on simulations. So we're showing where that boundary is here on this plot of yield amplification of about 30. The kind of light gray points are simulations that help us figure out where that boundary is. So what we're going to do is walk through now the various designs from the last several years and show kind of how we got to where we are now. So the initial designs were low adiabat plastic capsules in high gas-filled Hohlraums, and they had low hotspot pressure and energy. So these are the very first experiments back in 2011 and 12, and here's kind of where they sit in this hotspot pressure, hotspot energy space. We call this design the low foot, and they had fusion yields of about 2 kilojoules. And there were a bunch of things that were going on in this design. We had large amounts of laser plasma instabilities, and laser plasma instabilities can backscatter light back out of the Hohlraum, and that means it's not in the Hohlraum, keeping that Hohlraum hot, and so that reduces drive and velocity, which we saw was very important. There's also large symmetry swings. So we had a lot of trouble getting symmetric implosions in the low foot. You know, basically NIF are designed to have sort of 2 cones of beams. They're what we call the inner cone, which are the ones that come to the middle of the Hohlraum, and the outer cones that are near the laser entrance hole. And those inner cone beams have a long path length through the plasma in the Hohlraum. And we were having trouble getting those beams to the middle. And if they don't go to the middle, then what you end up with is an oblate or pancaked implosion. So we were able to use something called cross-beam energy transfer, which is a plasma process that lets you actually transfer energy between the inner and outer cone beams in the plasma by just putting small amounts of wavelength separation between those cones. And so that was successful at getting improving symmetry, but we ended up with large swings in symmetry. It wasn't symmetric at all times. We also saw mix, and that was mainly seeded by the tent. The tent is the structure that holds the capsule in the middle of the Hohlraum. Here at the bottom is a photograph of a tent, a capsule with a tent. I mean, think of it as you know, having 2 pieces of saran wrap surrounding the capsule that's holding it in the Hohlraum. And you know, here's a simulation, a 3D simulation by Dan Clark, showing what we think that implosion looked like. And the tent seeded these kind of sombrero-like perturbations that were at the top and bottom in this design. So it was later found that that capsule support tent was a major factor in disrupting the hotspot and preventing us from getting higher performance. So the high foot design increased the adiabat to reduce the capsule instability and also reduce the convergence. And the performance improved, but again, eventually we found a plateau there as well. So here's where the high foot falls on this hotspot pressure, hotspot energy plot. It's the green points. And so you see we've moved up in hotspot pressure and also in hotspot energy with the high foot. The high foot had fusion yields of about 27 kilojoules. And the way we did the high foot was to raise the temperature, Hohlraum temperature in the early part of the pulse, which is the part we call the foot. So here's a plot on the left of the radiation temperature as a function of time. The dash curve is from the low foot, and the solid curve is from the high foot, and you see we've increased the level of the foot. The net result then is that you shorten the pulse because you want to time shocks, and so this launches an earlier, faster shock early in time. So that improved the stability and allowed us to push to higher implosion velocity with less mix. The LPI and shape swings still persisted because the Hohlraum was essentially the same. And eventually, as we pushed to higher and higher velocity, simulations said that the tent actually started becoming a problem again in the high foot. So the tent caused it to plateau, and LPI still was a major problem, which resulted in energy loss and large symmetry swings. So one of the things we learned from the high foot was that maintaining high ablation pressure until late in the pulse was important. And we control that by coast time. So coast time is defined to be the time between the end of the laser pulse and bang time. So on the left, I show the laser pulse shape. This was actually for the pulse shape from the first high foot DT shot in black, and then the red bar indicates the bang time, the time of maximum compression of the shell. And you can see there's about a 2 nanosecond time gap between the time the laser turns off and the time that the capsule reaches stagnation, and that's what we call coast time. If you look on the right, you see that initially we just saw this empirically, that reducing the coast time improved performance. And you can see that on this plot of coast time versus stagnation pressure. And you can see that as we reduce the coast time, the stagnation pressure rose actually quite rapidly with changes in coast time of actually relatively small size. A few hundred picoseconds could make a big difference. One thing I should note is the longer laser pulse with the lower coast actually makes symmetry more difficult, because basically the way we reduce coast time is to lengthen this time at peak power. So we now have a better understanding of the impact of coast time, and Omar Hurricane has given many talks on this and written many papers on it. So in the high foot and low foot, we used high gas fill Hohlraums, and so then we moved on to low gas fill Hohlraums to reduce the laser plasma interactions that have been present in the previous designs. So here I'm showing just a cartoon of a section of a Hohlraum, just looking at a piece of the Hohlraum. Here's the Hohlraum wall, and the laser entrance hole is up here, and this is the capsule where it's blowing off as it's ablating, and the inner cone beams and the outer cone beams. So in the high density gas fill, we fill this Hohlraum with a relatively high density of helium gas. And that Hohlraum fill tamps the expansion of the wall and keeps the Hohlraum from filling with gold plasma. But what we found is it has high LPI. So you can see where the outer cone beams hit the wall, we develop what we call the gold bubble. And in the high gas fill Hohlraum, that gold bubble is kept relatively small by that gas density. But the net result was we found that we had lots of LPI. We already talked about cross-beam energy transfer, which we used to move energy from the blue beams, outer cone beams, to the red beams, the inner cone beams. But we also saw a large amount of stimulated Raman scatter, which backscattered light back out of the Hohlraum, which is, we want it to stay in the Hohlraum. We also saw signs of 2 omega P instability. So after the high foot, we decided to move to low gas fill Hohlraums, which are more radiation hydrodynamic dominated. And here there's not so much tamping, so this gold bubble grows much more rapidly and much larger until the point where it just cuts off the inner beams, and the inner beams can no longer get past it to get to the Hohlraum wall. And so it becomes a race to get the pulse into the Hohlraum before it fills with plasma. So the low gas fill Hohlraums are a good match with a diamond or high density carbon ablator, because those ablators are very high density. That leads to a shorter pulse because it just takes less time for the shocks to get through the ablator. So the diamond capsules resisted the tent, and it used a shorter laser pulse, and we saw performance improve. So there were actually 2 designs in this time frame, one we called HDC and one we called Bigfoot. And you can see that when we went to the HDC and Bigfoot designs, we've now again made a big jump in improving the hotspot pressure in these kind of pink salmon colored points. So the HDC and Bigfoot had neutron yields of about 55 kilojoules. They used the low gas fill Hohlraums, which reduced LPI and had better symmetry. They used the diamond capsules, which was more resistant to the perturbation from the tent. That allowed us to go to higher velocity. In these HTC capsules, though, we started to see a jet going through the hot spot at stagnation that was from the fill tube, that tube that we used to get the DT in. And here's a closer up picture of the fill tube. So in that time frame, we took the fill tube and reduced it from 10 microns to 5 microns. And that resulted in reduced mix and less radiative loss. So if you look at this plot, we've made a lot of progress, but if we want to get to this ignition region, we've mostly been moving up. And really what we need to do now is move to the right. And so the energy is still too low. So we need a bigger capsule, but we need to keep the pressure. We have to stay up here at high pressure, and we don't have any more laser energy. So this is a major challenge. So back in 2017, our program director, John Edwards, challenged Omar Hurricane and I to come up with a strategy for how to make the capsule bigger. But we have to keep a similar adiabat, stability, velocity, coast time, and symmetry, and do that all with fixed laser energy. So there's just one or two constraints on us there. So now if we look at this yield formula, we're basically going after this scale term, which also has a fairly high exponent. So we developed a strategy that we called the hybrid strategy, and hybrid stands for high yield, big radius implosion design. And basically, the idea is to put a much bigger capsule into just a slightly larger Hohlraum because we don't have the laser energy to make the Hohlraum much bigger. So here we show the HDC design. Bigfoot is similar, showing with a 910 micron radius capsule in a 6.2 millimeter diameter Hohlraum. Now we're going to put a 1050 to 1100 micron capsule in a 6.4 millimeter Hohlraum. And this is a design we call Hybrid E. The designer for HDC was Laura Burzak-Hopkins, and designer for Bigfoot was Cliff Thomas. For experimental leads were Sebastian Lepop and Dan Casey. For Hybrid E, the lead designer is Annie Kreitzer, and the lead experimentalist is Alex Zylstra. So we need to maintain a symmetric implosion with a larger capsule and with low coast to effectively couple that kinetic energy to the hotspot. So as part of the hybrid strategy, we started trying to better understand what limited the symmetry in these low density Hohlraums. So remember we said before, the Hohlraum symmetry is dominated by the inner beams being stopped by that gold bubble and by the expanding ablator. So back in 2018, I put together a model that tried to identify the parameters that were important to asymmetry. And here's a plot from that model. Sometimes people call this Debbie's plot. And basically what it says for this purpose is that if you go to a bigger capsule or a longer pulse to get a shorter coast time, you end up with a much more oblate or pancaked implosion. And so we realized we need some additional symmetry techniques if we want to drive around implosion with that larger capsule and a short coast time in that Hohlraum that's only slightly larger. So we developed two additional techniques for symmetry control, cross-beam energy transfer in the low gas fill Hohlraums and the I-raum geometry. So on the left, we show the hybrid E design, which is a cylindrical Hohlraum that uses cross-beam energy transfer. So just like we did in the high gas fill Hohlraums, we're going to detune the wavelength of the lasers between the inner and outer cones and transfer energy from the outer cone to the inner cone. And that means that we can basically get more energy to the waist of the Hohlraum as that gold bubble is expanding. This is a very powerful technique in these low density and these low fill Hohlraums. Here are some plots of X-ray images from experiments using gas-filled capsules. And you see when the lasers had the same wavelength, we got a very oblate or pancaked implosion. By just detuning the laser wavelength by 1 angstrom, we went to a slightly prolate or sausaged implosion. And so this is the technique that's been used in the hybrid E design. The second design was one we called the I-raum, which uses a shaped Hohlraum, and we actually ended up using a little bit of cross-beam energy transfer there as well. And the idea of the I-raum is, well, if the expanding gold bubble is the problem, let's just add some pockets on the side of the Hohlraum so that the gold bubble starts out further away from the inner beams. That'll give us more time to get the inner beams through. And so that is another technique that's worked to get symmetric implosion. And both of these two designs have produced a burning plasma in the last year. So we have two designs that get a burning plasma. So we talked about crossbeam energy transfer in the high gas fill Hohlraums, but it's actually even more powerful tool for symmetry control in the low gas fill Hohlraums, based on our current understanding. So in the low gas fill Hohlraums, we require a very small wavelength separation, much smaller than we did in the high gas fill Hohlraums. So in the low gas fill Hohlraums, we're changing the wavelength separation by 1 to 2 angstroms compared to 8 to 9 angstroms in the high gas fill Hohlraums. And so in the high gas for Hohlraums, this 8 to 9 angstroms, resulted in a very large amount of transfer in that foot, that early part of the pulse. And when I say large, I mean like 10 times. So we'd increase the inner cone by like 10 times its initial laser power. This led to swings in symmetry, which were difficult to control and predict. In the low-fill Hohlraums, we seem to see consistent scalings of P2 with CBET, although I will say we occasionally have surprises when we make other large changes. We can generally recover, though. So here's a plot showing the P2 where we've adjusted for the pulse duration and the delivered laser pulse as a function of that wavelength separation for all the hybrid EDT shots with 1050 capsules. And so we see that 5 of these shots actually lie on a nice straight line. But one shot where we used a thinner DT ice layer then jumped off that curve. And that's one of these examples where sometimes we see something that we may not have expected to change the symmetry that does. Okay, because there's a trade-off between capsule size, symmetry, and coast time, we actually expected there to be an optimum capsule size. So just looking at this cartoon here, what we expected to see was that, as we increase the size of the capsule, the yield would increase with the scale, based on this formula on the right. But then at some point we would lose control of the asymmetry, the instability, or the coast time would become too large, and then the yield would start to go down. And since we didn't know where this optimum was going to be, the plan was to use different capsule sizes and find that optimum experimentally. So the initial hybrid E used the largest capsules and increased the hotspot energy, but the pressure dropped, the capsule quality degraded, and we got mix. So here's where the initial hybrid E and I-raum points fell on this plot. So we did what we wanted in that we got the hotspot energy higher, but we lost our high pressure that we had been getting in HTC and Bigfoot. And the yields are basically the same, about 55 kilojoules, which you can kind of see because these are sort of equidistant from this ignition curve. So we increased the size of the capsules from 910 to 1100 micron radius. We got more coupled energy, but we got a longer coast time because it has a longer distance to travel with a larger capsule, you end up with a longer coast time. Unexpectedly, we also saw that the ablator quality degraded when we went to the larger capsules, which we didn't expect. We were just making a small change in size, but we started to see pits on the surface of the diamond ablator and voids in the bulk of the ablator. And those seed mix and resulted in the lower pressure that we saw in the experiments. We did try thickening the ice layer to protect from those defects, and that helped at low velocity, but it really wasn't enough. So recovering the pressure and temperature would require us to get lower coast and less mix. So slightly smaller capsules reduced the coast time, and we got some capsule quality improvements, and the performance improved markedly. So here's where the hybrid E and I-raum 1050 capsules fell. Now you can see we've got the hotspot energy we wanted, but we're back up in pressure. And these had a maximum yield for these shots was about 170 kilojoules of fusion yield. So we've reduced the coast time, we've got higher pressures, and at the same time, our target fab colleagues had been working very hard on trying to understand and improve those capsules. Why did we start getting these features and how do we fix that? And so we got better capsules. We also increased the dopant and saw less mix and higher temperatures. And we were able to reduce coast time here from about 1.5 nanoseconds to 1 nanosecond. And based on the high foot data, we thought we should start to see some improvement based on that reduction in coast time. So while it wasn't confirmed, the analysis suggested that the coast was still suboptimal, which motivated tests of yet lower coast. Okay, so to reduce the coast time further, we had to make the Hohlraum even more efficient, and we did that by reducing the laser entrance hole size. So remember, we can't reduce the coast time by just putting more laser energy because we don't have any more laser energy. We've already tapped out the laser. So we modified the hybrid E design with a smaller laser entrance hole. We took the laser entrance hole from 3.65 millimeter to 3.1, and Joe Ralph led a campaign called Hohlraum scans that did the work to do this reduction. So by reducing the laser entrance hole, we reduce the radiation losses, because remember, this Hohlraum's like a little X-ray oven, and so these are just holes, and so the X-rays are just leaking out these holes, and so by making the hole smaller, we reduce those losses. So reducing the losses means we can get the same temperature in the Hohlraum with lower laser power. And so we reduce the laser power from the blue to the orange using this smaller laser entrance hole. But then we can take the energy that we saved here and we can tack it on the back of the pulse and reduce the coast time, which is what we did. And that allowed us to reduce the coast time by another 350 picoseconds. And now we're starting to get into the steep part of the curve based on the high foot data. And there still may be room to make further improvements in this design. And actually in the next year, we're going to be trying to reduce this laser entrance hole even further. So the first DT shot using that smaller laser entrance hole was N210808, which produced 1.35 megajoules and the highest yield amplification of any shot to date. And here's where that hybrid E shot sits in this space, producing 1.35 megajoules by using reduced coast, and it got higher pressure and we had better stability in this case. So there were other important improvements in this shot. The laser team has been working very hard on making laser improvements to give us better precision energy delivery of the pulse shapes that we need. We mentioned the capsule quality before. 210808 was the highest quality diamond capsule we've ever shot. So this is a picture from some of the previous shells where we had these voids in the center and high Z particulates, and this shot did not have those. We also reduced the fill tube from 5 microns to 2 microns, and these together give us less mix and higher temperature. And so future experiments, in fact, some that we're already starting, help us understand the relative importance of these changes. So at the threshold of ignition, small changes in the no alpha space can lead to large changes in the real alpha on space. So we've been talking in this space where alpha deposition is turned off. If we now look at the same plot in the alpha on space, you see that we've made this huge leap in hotspot energy and hotspot pressure with a yield amplification of about 30. And a much higher pressure and energy with small changes to those input conditions really indicates that we're in a new regime. And many of those key experimental measurements are pointing to this implosion being a fundamentally new regime. We've talked about the yield and the temperature. The hotspot mass also made a large jump. The hotspot energy made a jump. We also saw that the burn width got shorter and the neutron radius got bigger. And all of these are signatures of a hotspot that's undergoing a rapid self-heating and beginning for that burn to propagate into the surrounding dense shell. So 2D post-shot simulations capture many of the important implosion performance metrics in this new regime for this new design. So we do simulations. We start by doing integrated hydra simulations where we do a simulation that includes the Hohlraum, the lasers, and the capsule. But this is at relatively low resolution in order to model all of those processes. So we can take out that temperature source from this Hohlraum simulation. Oops. And put that into a capsule-only simulation where we can include surrogates for the tent and for the fill tube. And if you look, these 2D simulations that use a model for the degradations that's benchmarked against previous shots do a pretty good job of getting many of the important metrics. People often ask about the pre-shot. The pre-shot predictions showed an increase of 3x in neutron yield, but that was actually below the data, which is almost an 8 times increase. But the post-shot includes the as-delivered laser, which did deliver a little bit high on that shot, the 2-micron tube, which was not included in the pre-shot, the observed asymmetry, and then we get something like 20% in yield. And Annie Critcher and many others have been doing simulations of this shot. So to remind you, to get ignition, which is a thermal instability, we have to have that alpha heating greater than all those energy losses. So we talked about this earlier. We want the alpha heating to be dominating over the X-ray losses and the thermal conduction losses in order to get this thermal instability. So if you look at the scalings of these losses and the alpha heating, you see they're all functions of rho r and t. So it's actually interesting to look at these implosions in rho RT space. So let's do that. So the previous 55 kilojoule experiments had alpha particle heating, but not enough to overcome the losses. So here we're plotting from a simulation the trajectory of the hotspot in that temperature rho R space. And this dashed curve is the static self-heating curve where alpha heating just balances conduction and radiation losses. So what happens is the hotspot rapidly heats, and then as it compresses, the rho R goes up as it compresses. And for this 55 kilojoule experiment, it just crosses over into this boundary, but then it starts to expand and on explosion and cools and goes to lower density. Oops. For some reason, this thing's starting to move on its own. For the 170 kilojoule shot, the alpha heating dominates the implosion, and it shows an increase in temperature, but it's just not enough to overcome the losses. So here, again, we heat and then we start to compress. It goes deeper into this region, but it's not enough to keep heating, and so it eventually fusion loses and it disassembles. But for N210808, we see a substantial increase in the calculated temperature and the rho R, and we see a reversal in this rho R TIN trajectory. So again, we see it heating and compressing, but now instead of turning right and coming apart, we see it turn left, and it continues to heat and go to higher density now that fusion is actually winning. And eventually, of course, it falls apart. So we're now in a new regime where alpha energy is completely dominant. For this shot, our estimates of the alpha heating energy is 250 kilojoules. The PDV work done is about 20 kilojoules. The radiation loss about 60 kilojoules. And we got 1.35 megajoules, 15 petawatts of fusion power for 90 picoseconds. Okay, so what about ignition? Well, we don't actually measure the hotspot power balance directly, but there are several published metrics for inferring ignition, and we're evaluating this shot against all of them. I don't have time to go into it, but here are 4 different published metrics, and we pass all of these metrics. However, in 1997, the National Academy of Science did a review of the ICF program, and they defined ignition as gain equals 1. So we've talked about ignition as a statement about power balance in the hotspot of the implosion, but the National Academy decided to use a definition that's not about the power balance, but about target gain. I mean, the nice thing about it is it's super easy to evaluate, but they defined ignition to be target gain equals 1, and that is where the fusion yield is equal to the laser energy. And this shot is target gain 0.7, so we don't pass by that metric. Okay, we did the first shot to assess the variability of this on October 24th. We got 430 kilojoules of yield. Here's where it sits on that same yield temperature plot. This was the second shot with capsule gain greater than 1 and a yield greater than 10 to the 17 neutrons. That is super exciting, having been in this program when we couldn't get 10 to the 15 neutrons, or we struggled to get 10 to the 15 neutrons. We're still doing data analysis and simulations. We do expect variability near the ignition cliff, and I'll talk about that in the next few slides. We did observe a large mode 1 in this experiment, where we could see that the hotspot is actually moving downward in the chamber at about 130 kilometers per second. N210808 was about 68, so it's about moving about twice as fast. And you see that in these yield detectors, the fuel is thick on the top and thin on the bottom, which is not really what we want. So near the ignition cliff, we do expect variability. The designs are very sensitive to the input parameters, and the sensitivity actually increases with yield amplification. So, here's kind of a cartoon. Because it's a threshold process, we expect sensitivity to increase with the higher yield amplification. And we don't quite know where we are on this curve, but we do know that when you get close, you can make small changes in the inputs and have large changes in the outputs. And here's an example from simulations by Annie Kreitcher, where she did 2D simulations of 210808, showing a strong sensitivity to that mode 1 that we saw in the previous slide, and basically 2x in yield from between 210808 and the repeat. And our ensembles team, including Luke Peterson here, have been doing 1D simulations looking at variability, and they can easily see plus or minus 25% variability in yield just from 1D laser and target variations. So since APS, we've done 3 experiments testing the variability, including the one I just talked about. All have reached greater than 10 to the 17th and capsule gain greater than 2. None have exceeded 1.35 megajoules, but they are well beyond the early 2021 shots. So here's that plot now, including all of those shots. Showing the most recent shots. And here it is in a different metric, p tau, which is another metric towards ignition. And you see that we're kind of filling in that ignition cliff. So the variability that we see in these shots is mainly attributed to the larger unintentional odd mode, that P1 implosion symmetry, or more mix. So here are the 4 shots that we've done, the 210808 that we've been talking about. These 2 had larger hotspot velocities and lower yields. One of these, interestingly, had the 5 micron tube. It's actually the second highest yield, used the 5 micron tube. And the other shot had actually low hotspot velocity, but showed a large amount of hotspot mix into the hotspot. So of course, we're working on understanding and mitigating these degradations to improve the robustness. So just to summarize, our August 8th NIF shot, N210808, yielded more than 1.3 megajoules, and this marks a significant advance in ICF research. We got capsule gain greater than 5, laser gain of about 0.7, about 2% of the fuel was burned up, and 13 times increase in fusion yield since the last APS meeting. And we've been waiting for this since Knuckles' 1972 Nature paper. So of course, while we've made progress, there is work that still needs to be done. We want to understand better where we are, assess the variability, which we've started, as you just saw. We want to assess the sensitivity to the input parameters and do those dudded fuel experiments to validate our models in this yield amplification range. And of course, we'd like to push to higher performance, higher compression, more laser energy, which we may be able to get out of NIF, and make further improvements to the Hohlraum. And then we'd like to use the current designs for science experiments. The output of this implosion is the most powerful energetic driver we have for HED. And we also want to continue improving our simulation capabilities. And this is a very exciting time for our field. So I hope everyone appreciates, how great it is and how fun it is right now. And with that, I can take any questions.
Thank you very much for the wonderful talk. So first, I'd like to thank with an applause, and the electronic applause too. If you have any questions, please enter them in the chat field, or you can enter a queue if you want to ask it verbally.
I see someone raised a hand. I can't quite see because my screen is.
Linda Lodestro would like to ask a question.
Sorry, I didn't quite follow your instructions. I didn't get the cue in. Could you go back to slide 46, please?
46. Yes.
Yeah, so early when you said ignition, you have to fusion beat the losses for a duration. Of course, I'm wondering what duration, what does it scale to and stuff. So this plot here helps a lot to
Right.
understand what the issues are. Uh, with the, you had another curve there.
Oh, let me go back one more. There it is.
Oh,
I think that's
sorry.
the one you're looking for.
Yeah. It looks very tempting to try to find a condition from these curves, maybe like the volume of the region above that equal, the dashed line, or the slope at which it
Yeah, and
crosses, or
people have been doing that. I think there's a model by Paul Springer and Jim Hammer that looks at kind of the second derivative of the temperature, right? If we go back to this, whoops. Maybe if I don't know if one of those guys is on, they can maybe describe it a little bit more. But that has to do with whether we're turning right or turning left.
yeah, yeah. Oh,
Absolutely, yeah, absolutely.
okay. And can I squeak in another question?
Sure.
Diamonds sound expensive for IFE. Is it too expensive for IFE, or can you replace the diamond?
So this is not diamond like a diamond ring. It's more like an industrial diamond. I don't know about the cost. That's something we certainly would have to look at. When I used to work, as Paul said at the beginning, I used to work in IFE, and so you really have to look at the materials and the cost of materials and how to get the materials out of the chamber and all those kind of issues if you're going to do IFE. So yeah, I mean, I think this is my personal feeling. This is huge step for IFE, but we're still a long ways away. I mean, we had to make this happen in order to get IFE, but there's still a lot of work to be done there.
Okay, thank you.
Mm-hmm.
Any other questions?
Can I ask a question? What code is used to simulate the shots?
Most of the simulations that I showed today were done using Hydra, which is our 3D Rad Hydro code. There's also people who use Aries and Lasnix.
Thank you.
Uh-huh. This thing seems to be moving on its own.
Okay, there's a question from Jürgen Biener. The diamond shell material, oh sorry, it's a comment. The diamond shell materials costs are less than $1 per shell.
Yeah, I think for IFE though, it's got to be quite a bit less than that. But that kind of depends on the whole system. Thanks, Jürgen.
But small compared to the total cost of these shots by far.
Right. But for IFE, right, it has to be small compared to the
Yeah.
cost of energy that you're producing. And so, it just has to be worked out.
In years past, the cost of the whole target, I thought, was 10 cents for IFE.
I think that depends on the design and how much gain you get from the design. So I think there's a range. $1 sounds a bit high, but yeah. So someone needs to look at the integrated system. We have used plastic as well, and so there are other options. We've settled on diamond right now, but we are still looking at plastic. And there are other ablator choices, but plastic is probably the cheapest. That's kind of a guess.
So I have a question. What physics experiments would you like to do being able to reach this new regime?
So actually, there's a whole working group that's been stood up to look at what those experiments could be. But we can certainly do experiments trying to study mix and trying to study opacities and properties of materials. There's a group that's been stood up, and I think they're going to have a workshop next year to discuss that.
And there's a question from Derek F. Does the use of diamond in the shell in some way accidentally focus the laser energy acting as a form of a lens?
Well, I don't know necessarily diamond. There is refraction of the laser beams off of the ablator material, and that does change the direction that they're going. We especially used to see that in the simulations of the high gas Hohlraums, where the laser beam was trying to propagate through a very high density, and so a channel would form in the plasma, and the beam would basically be refracted into that channel. And that happened in plastic as well. I think it was just a function of the density rather than the material, I believe. How important is the ice layer quality? That's a great question that we're trying to understand. We have had some shots where we've had large grooves in the ice layer. There's at least one or two where we think that did impact the performance, but I think that's a question we still don't completely understand at this point.
Any other questions? Well, if not, oh, there's one more from Doug Speck. Are shocks a tool or a necessary evil?
So we use shocks to, basically adiabatically, gently accelerate the shell. And so I'm I'm not sure if they're evil, but they are used in order to control the adiabat of the implosion, and as we want to compress it, keep it to the adiabat that we want.
Okay. So thank you again for this great talk. We will be taking a break for a few weeks for the holidays, and hope to see you all back in January. And otherwise, please let's thank our speaker again.